Let's talk about securing network traffic. As we've seen, encryption is used for protecting data both from the privacy perspective and the data integrity perspective. A natural application of this technology is to protect data in transit. But what if our application doesn't utilize encryption? Or what if we want to provide remote access to internal resources too sensitive to expose directly to the internet? We use a VPN, or Virtual Private Network Solution. A VPN is a mechanism that allows you to remotely connect a host or network to an internal private network, passing the data over a public channel, like the internet. You can think of this as a sort of encrypted tunnel where all of our remote systems' network traffic would flow, transparently channeling our packets via the tunnel through the remote private network. A VPN can also be point-to-point, where two gateways are connected via a VPN, essentially bridging two private networks through an encrypted tunnel. There are a bunch of VPN solutions using different approaches and protocols with differing benefits and trade-offs. Let's go over some of the more popular ones. IPsec, or Internet Protocol Security, is a VPN protocol that was designed in conjunction with IPv6. It was originally required to be standards compliant with IPv6 implementations, but was eventually dropped as a requirement. It is optional for use with IPv6. IPsec works by encrypting an IP packet and encapsulating the encrypted packet inside an IPsec packet. This encrypted packet then gets routed to the VPN endpoint, where the packet is de-encapsulated and decrypted, then sent to the final destination. IPsec supports two modes of operations, transport mode and tunnel mode. When transport mode is used, only the payload of the IP packet is encrypted, leaving the IP headers untouched. Heads up that authentication headers are also used. Header values are hashed and verified, along with the transport and application layers. This would prevent the use of anything that would modify these values, like NAT or PAT. In tunnel mode, the entire IP packet, header, payload, and all is encrypted and encapsulated inside a new IP packet with new headers. While not a VPN solution itself, L2TP, or Layer 2 Tunneling Protocol, is typically used to support VPNs. A common implementation of L2TP is in conjunction with IPsec when data confidentiality is needed, since L2TP doesn't provide encryption itself. It's a simple tunneling protocol that allows encapsulation of different protocols or traffic over a network that may not support the type of traffic being sent. L2TP can also just segregate and manage the traffic. ISPs will use L2TP to deliver network access to a customer's endpoint, for example. The combination of L2TP and IPsec is referred to as L2TP IPsec and was officially standardized in IETF RFC 3193. The establishment of an L2TP IPsec connection works by first negotiating an IPsec Security Association, which negotiates the details of the secure connection, including key exchange if used. It can also share secrets, public keys, and a number of other mechanisms. I've included a link to more info about it in the next reading. Next, secure communication is established using encapsulating security payload. It's a part of the IPsec suite of protocols, which encapsulates IP packets, providing confidentiality, integrity, and authentication of the packets. Once secure encapsulation has been established, negotiation and establishment of the L2TP tunnel can proceed. L2TP packets are now encapsulated by IPsec, protecting information about the private internal network. An important distinction to make in this setup is the difference between the tunnel and the secure channel. The tunnel is provided by L2TP, which permits the passing of unmodified packets from one network to another. The secure channel, on the other hand, is provided by IPsec, which provides confidentiality, integrity, and authentication of data being passed. SSL TLS is also used in some VPN implementations to secure network traffic as opposed to individual sessions or connections. An example of this is OpenVPN, which uses the OpenSSL library to handle key exchange and encryption of data along with control channels. This also enables OpenVPN to make use of all the ciphers implemented by the OpenSSL library. Authentication methods supported are pre-shared secrets, certificate-based, and username password. Certificate-based authentication would be the most secure option, but it requires more support and management overhead since every client must have a certificate. Username password authentication can be used in conjunction with certificate authentication, providing additional layers of security. It should be called out that OpenVPN doesn't implement username password authentication directly. It uses modules to plug into authentication systems, which we'll cover in the next module. OpenVPN can operate over either TCP or UDP, typically over port 1194. It supports pushing network configuration options from the server to a client, and it supports two interfaces for networking. It can either rely on a Layer 3 IP tunnel or a Layer 2 Ethernet tap. The Ethernet tap is more flexible, allowing it to carry a wider range of traffic. From the security perspective, OpenVPN supports up to 256-bit encryption through the OpenSSL library. It also runs in user space, limiting the seriousness of potential vulnerabilities that might be present. There are a lot of acronyms to take in, so take a minute to go over them and read more about them, and I'll see you in the next video.